Well, we talked a little bit about sound earlier, and I'm very pleased that we're going to dig deep into that now. And I'm going to introduce to you Doug James, who's a professor of computer science at Stanford, and has been studying computer graphics, computer sound, physically based modeling and animation, and reduced order physics models. So if you think of what are the physics of sound, Doug is the right person to ask. Thank you.
Thank you. Hi. I'm going to tell you about basically what I think is the future of sound and simulation. So by the time I retire, I expect things to be highly realistic and compelling. And so this is the kind of work that we're doing to make this happen in the future. So if you smash something on the floor in a virtual environment, I want that to be a complete integrated and synchronized event where the visuals and the physical motion and the sound that's generated are computed on the fly and are as most compelling as possible. In order to do that, you're not just going to play some canned sound effect, because who knows how somebody's going to smash something at some point in the future. And you don't want to store everything. You don't even know how to retrieve it. So you're going to compute it all on the fly, and it's going to be great. So that's what I want to see happen. So just a little about me. I'm a new professor at Stanford. My background is in applied math and physics and robotics and computer science. I'm interested in a lot of things. I do computer graphics, I would say, but I do much more. I was actually the technical papers chair of SIGGRAPH, which is the largest computer graphics conference in the world. I'm really interested in simulation of all things visual. And anything to do with the senses in particular. So being able to simulate cloth at incredible resolution so that you can see how every little yarn in a piece of cloth stretches and wraps around when it collides with something, that's a lot of fun. Being able to simulate content. If you've ever tried to knit a sweater in virtual reality, it's a complete disaster. So use physics to get the detail for you. It's a lot easier. Other things I've done like visual effects. So this is like a method we invented to produce a lot of turbulence and fire and smoke and things like that. There have been a lot of movies that you've seen. We've done stuff like that. I really am excited by simulating contact and doing it efficiently. So being able to simulate this ball. So my wife gave me this ball when I went on sabbatical, and she said, here, maybe you should relax a bit. And I said, I'm going to simulate that ball. And then we used it in our paper and got this 10 times speed up over prior methods. I also like to simulate things really fast. And so if you can simulate things really fast, you can also simulate lots of them. So like I guess about over a decade ago, this is something I simulated in a Java applet using a lot of billions of collisions. One nice thing about simulating things fast is then you can do them interactively for sensory feedback. So for haptic rendering, so I've been doing haptic rendering since the 90s when computers were really, really slow. And they're still really slow, I think, today. But one way to make them faster is to try to do stuff ahead of time, pre-compute physics, build data structures ahead of time, and then use that to display touch at kilohertz rates, or to do sound really fast. And so here's like a demo of the sound. There's no sound, right? So why is there no sound? Because so many people are obsessed with the visuals. The visuals always come first. It's always been like that, right? And we keep repeating this over and over again. So in simulation, people focused on how to get the visuals right, how to get these motion. We need to get these great physics-based animation shots for the movies. But what about the sound? It's basically like Edison, right? We make these great visuals, and then, we show them to people, and then we go, oh, we need the sound, oh, add the sound in later. It's like, add some text, that's the first. And then you just, after that, then you make some sound effect and add it in. Somebody adds it by hand, right? There's nobody inside your computer adding it by hand in virtual reality, right? It has to be done automatically. So you need a program to do it if it's going to be synchronized and really good. So this is the basic goal that we set out to do. Whenever you simulate something, whatever it is, say this bottle hitting the ground, there's some disturbance, a vibration or some acceleration that makes the air want to move. And then from that, there's a sound field, just like Gordon talked about light fields that our eye wants to experience. Our ears want to experience sound fields. They're rich three-dimensional structures. And we're going to convolve that field with your head or with the surrounding environment, and that's going to provide your listening experience. That's what's going to be piped into your ears along with your head-mounted display. And that's what's going to make it seem like more than just a visual experience with bad sound. It's going to be all computed at once, and it's going to be the sensory stream. OK, so we started working on trying to extend animation with sound. And we said, well, what do we need to do? Well, there's all these things we animate. So we just started trying to do some of them. Fluids, fracture, all these different things. I'll show you some short videos of them. But basically, we wanted to fill this black hole where we could animate things, but we didn't have sound models for them. So we had to address all the different types of phenomena we could animate. Let's go and try to figure out how to fill in the stuff between the frames. That's what sound does. And then we had all these algorithms and details to figure out. In the end, we wanted it to run really fast in parallel. We wanted systems which we could evaluate on GPUs or what have you and run them quickly for VR. That's our goal. I'll just show you some examples. So this is kind of stuff we do. So one thing that we can do really well is rigid bodies, stiff objects that hit the ground and vibrate like this plate. So these kind of things run in real time. We can have lots of them. Other things we do are objects that make really noisy sounds, like shells, like a garbage can. It doesn't make a dinging sound because it vibrates chaotically. So we can simulate these and get really grungy, noisy sounds. So we have a lot of methods for reduced order modeling and fast simulation of these nonlinear vibrations. Other thing that happens is objects, they smash, right? So we're smashing stuff all the time. In fact, computer graphics and animation professionals are basically destructive personalities that just blow up San Francisco every summer. You know, it's the same thing. So how do we add sound to all these fracture events? And so basically, when an object breaks, it produces lots of little rigid body sound models if it's brittle. So all the sounds are synchronized because they're computed with the picture. They're not separate. They're one thing. We can also look at combustion. When gases are heated, they expand. That makes a pressure wave. So we can use methods for computational fluid dynamics and combustion and use that to compute sound sources and then generate sound. It'll seem real when it's right in front of you, but it won't burn your hands. The other thing we looked at is how these vibrations couple together. So when you bang on a table in a virtual environment, if they're all simulated as rigid objects, then they behave rigidly. So the table rigidly resists, and that's it. But if you bang on a table, at your dinner table, everybody's plates are going to move, right? So we can capture these couplings between the vibrating objects so that everything is connected. Another thing we realized is that really tiny objects behave differently. They don't vibrate and produce sound like big objects, like a plate. They hit things and they instantaneously change direction. They make a little pulse of energy, a little click. And there's a lot of detail in these clicks that you can resolve. So if I throw some dice on the table, you'll hear the table make a sound. But really what you're missing is all the sound of the dice. And then at the end, I'll play all three together. That's just the table. But that's the missing sound. So when we add all these little bits together, then we get these more hyper-realistic sounds. And they're not just like a wave file. They're actually a full sound field we can evaluate anywhere at anybody's listening position in a virtual environment. So we found ways to speed up these things so we could have lots of objects. And so then you could do tons of little bits of rubble as you kick around on your feet. And then when we add this to the fracture, we get these hyper-realistic little bits of debris that you can listen to from anywhere. We have stuff for cloth, too. Characters need sound. I call this the drunken boxing demo. It's like a VR demo where you have binaural headphones on, and it's rendering your clothing sounds from that viewpoint. This one already makes me sick, even without the headset on, though. Okay, another thing that we're really, really excited about is fluids. There's so many types of fluid sounds. People are pathologically, they want to see lots of fluid effects and stuff, right, in movies, and they're made of fluids, you can't blame them. So how do you simulate water realistically? So we can pre-compute water and display it or make it run really fast. How do we compute like the sound of air blowing around your ears? Or like if you pour a glass of wine and ding it and swill it around, you get this sound. How do you get that stuff? We should be able to do that, right? We know physics. F equals ma, right? So we can go ahead and compute all these things. That's what we're trying to do. Here's a result we did a while ago on simulating bubbly sounds from Babbling Brook. This model actually hallucinated most of the bubbles with a randomization process. But more recently, what we've been doing is we've actually been trying to use parallel algorithms to actually resolve all of the interface effects of how the bubbles pinch off and split and merge and be able to compute high-resolution fluids. And then if we really knew what we're going to do, maybe we could actually compute the sound for these too. And so here's some of the very first results that we've done with these high-res solvers. So now we're scaling this up to do much larger effects, all from first principles. Another problem we have is the sound models are all these 3D sound fields, so they can become quite complicated. The bigger the objects are, the more stuff they have. So this backhoe bucket has like 500 modes and takes up about half a gig. And it's really all these vibrations it has. And so how do you deal with all this data? So one problem you have, just like you have videos need compression, audio needs compression, 3D sound models need compression. And so there's whole families of methods for compressing these different types of simulation models that we need to come up with. But there's different things you can do. One way we can do is we can basically compress these displacement fields of how the objects deform using fewer bits. We can exploit symmetry of how these objects vibrate and also human perception to ultimately compress things down significantly. And you can go even further if you're willing to introduce noticeable differences. But here's a difference between like a 200 meg model and a 3 meg model. So there's basically no difference. And if you go even further, you can get it squished way down. Another thing that we're doing is not just looking at simulation, but also capture and how you can actually use sounds to, in a virtual Foley scenario, to actually estimate motions which match sound, and basically related to robot sound or being able to think or hallucinate what motions match sound. So if I threw an object across the stage here, you could have your eyes closed and still know there was an object going across the stage, and you could probably guess what it might be doing. So we built a program that could do that. It could dream about motions that match sound. So on the bottom is a sound timeline that has some events where this particular object, a wrench, bounced on the ground. And what we did is we wrote a program to search the space of all possible motions to find motions that were synchronized and had the same physical amplitudes of impacts as this. And then we gave it a whole bunch of sounds for known objects. And then it was able to produce movies that synchronized with these sounds. Basically, it could dream up what these sounds were and what the motions were. So we didn't have to write a simulator for garlic sounds. We just used some data. So in reflections about this approach, basically I'd say that we've done a bunch of different things. We've shown that it's possible to animate and simulate sound for a wide range of visual effects. But there's still so many things to improve to make it better. And we also want to make it faster. Plus, we need funding and we need partnerships to actually make this a bigger endeavor. So basically, the main focuses going forward are better simulation algorithms always. We want to do fluids realistically. We also want to do things fast. We want to make things run in real time. Not everything can be simulated in real time, but we can simulate some things ahead of time and then display it. There's the whole content creation problem. That's a big deal. You've got these 3D sound fields. How do we make it so we can stream this in real time? How do we display humans? Humans are interesting sound sources. You don't just make a point source and play voices out of it. It doesn't sound right. So how do you capture all of what it's like to actually have a shared experience with another person in a virtual space and make it sound really good? And then putting this all together, how do we simulate and capture things, combine simulations and captured content, pre-compute it, and make it work really, really well? This is my son. The first time he tried an Oculus headset, and he thought it was pretty cool. And I asked him what it sounded like after, and he said, well, it sounds pretty bad. And so hopefully by the time I retire, we'll have much better sound. So thank you very much.